In this video, we're going to talk about another class of reactions that alkyl halides undergo. And I apologize ahead of time. This video is a little bit longer than I'd like, but there's kind of a lot going on in E2 reactions. So when we talked about SN2 reactions, we mentioned the fact that alkyl halides can undergo both substitution, which we saw in SN2 reactions, and another type of reaction they can undergo is elimination, where we remove the halogen and a neighboring hydrogen atom to make an alkene. And so one type of elimination reaction is going to be the subject of this video. So when an alkyl halide is treated with a strong base, it can undergo beta elimination, right, where we're removing the halogen and then we're removing a hydrogen on one of the beta carbons. And a strong base will react in a concerted mechanism called an E2 elimination. And in another video, we'll look at another type of elimination called an E1 elimination. But much like the SN2 reaction, an E2 reaction is a concerted mechanism. So we have two things going on at the same time. So we have a proton transfer where our strong base is stealing the hydrogen, and at the same time we have the loss of a leaving group. And the electrons that form the carbon-hydrogen bond, those become a double bond between the two carbons that are losing the halogen and the proton. And so the name E2 comes from the fact that this is again a bimolecular reaction, because both the alkyl halide and the base are involved in this concerted mechanism. The rate of the reaction depends on both. And so because it's second order or bimolecular, that's where the name comes from. So it's a second order elimination reaction. When we talked about SN2 reactions and we looked at the effect that the substrate had, the trend was that primary alkyl halides tended to react faster than secondary alkyl halides, which reacted faster than tertiary alkyl halides. And tertiary alkyl halides, oftentimes weren't reactive in SN2 reactions at all. It turns out E2 reactions, the situation is different. Right? When we have a big bulky group, right, nucleophilic attack is hard because the nucleophile can't get into the carbon. But in elimination reactions, because the base is attacking a hydrogen on a beta position, even if the substrate is sterically hindered at the alpha carbon, as long as the base can get into the hydrogen that's on the beta carbon, the E2 elimination can occur. Now, it's very common for a substrate to have more than one beta carbon, and therefore multiple products are possible. In the case of this molecule, right, we're going to lose this bromine, so this is our alpha carbon, so any hydrogens on beta carbons are available or possible for elimination. And so I have, right, a CH2 here, and then these methyl groups would yield the same product because these are, essentially identical methyl groups. So we can either get this product where we took a hydrogen off of this beta carbon, or we can get this product where we took a hydrogen off of this beta carbon. And so we can rationalize the major product and the minor product based on the stability of alkenes that we talked about in a previous video. This is a tri-substituted alkene, and we expect that to be more stable than a di-substituted alkene. So this is what we would expect to be the major product. When we have reactions where there's more than one possible constitutional isomer that are products, and when one of them is preferred over the other one, we call this regioselectivity. And so we would say, in this case, this E2 reaction is regioselective. Now, it is possible to get the Hofmann product, the less substituted product, and we can do that by using bulkier bases. So this ethoxide ion, right, just has an ethyl group, 2 carbons here, right? It's not particularly big, and so it can get into the more substituted beta carbon here easier. When I start taking really big, bulky groups like these, that actually makes it harder for this big, bulky base to get into this carbon atom. It's much easier for it to attack over here where there's sort of, less carbons coming off this guy. And so big bulky bases can actually favor the Hofmann product, the less substituted alkene. All right, and so just to sort of re-emphasize what we talked about on the previous slide, a sterically hindered base can favor the Hofmann product, the less substituted alkene. And so sterically hindered bases can be very useful in controlling reactions and getting the less substituted alkene as a product. I don't think you have to have these memorized, but this one is going to show up a lot. And when we want to have an example of a bulky base, this is often the one that we choose for an example. So, this potassium tert butoxide, when you see TBUOK, right, this is what we're using for a bulky base. All right, so let's look at a couple examples. So we want to predict the major and minor products for each of the following reactions. So what we need to do is we need to identify the beta carbons and see if they have any hydrogen atoms. So in this first molecule, I think I have hydrogens here, and I have hydrogens here. I also have a beta carbon here, right? But this has got 4 bonds to carbon. It doesn't have any hydrogens, so it can't. We can't put the double bond here because there are no hydrogens here. So we can either put we have a product where we can get the double bond here, or we can get the double bond here. And so my two products are there, or I can get the double bond here. And now deciding which one is the major or minor product. So we don't have a bulky base, and so we're going to prefer the more substituted alkene. And so this should be our major product. Well, this one should be the minor product. All right, we have a second example. And so I'm looking for beta carbons that have hydrogen atoms, and so I have here and here, although these two methyl groups are equivalent, so they'll both produce the same product. And then I have the beta carbon here, so I could get a double bond here. So we have a couple different options. So that would be pulling off, right, the iodine, and then one of the hydrogens on this carbon, or I can get a double bond here. All right, and now in this case, I have, again, di-substituted versus a tri-substituted, and so I would expect this to be my major product and this to be my minor product. All right, and then our third example, we have the same alkyl halide, and so we have sort of the same two options. Right, but in the first case, I had hydroxide as my base, right? That's not bulky at all, so that's going to prefer the more substituted alkene. In this case, I've got that butoxy as my base, right? And so this really bulky base is going to prefer the less substituted alkene, right? Because it's easier to get in here to this methyl group than for this big tert-butyl guy to get in here on this secondary one. And so for this case, with the bulky base, the Hofmann product is going to be my major product, and the Zaitsev product is going to be the minor. Okay, in the previous examples, we looked at regioselectivity, where I can produce different constitutional isomers. On this slide, we're going to consider what's called stereoselectivity, where I can produce more than one stereoisomer. So with this alkyl halide, it doesn't matter whether I take hydrogens from this beta carbon or this beta carbon. These are equivalent, and so it's going to give me the same products. But in this case, I can produce either the trans isomer or the cis isomer. And when we talked about the stability of alkenes, one of the things we talked about was that the trans isomer is generally more stable than the cis isomer. So in this case, we'd expect the trans alkene to be the major product and the cis alkene to be the minor product.